Hi, everyone. Thanks for taking the time today to attend this talk, where I'll give you an overview of how Grammarly's Android keyboard works. My name is Tushar, and I'm on the Android team at Grammarly, and I've been at Grammarly for about 2 years now. So thanks for joining. Um, yeah, let's get into it. So for those who are not familiar with Grammarly, Grammarly is an AI-powered writing assistant that helps you make your communication clear and effective wherever you type. Um, and the company's mission is to improve lives by improving communication. And where we see ourselves as our vision is building a comprehensive communication assistant that helps people connect wherever they are communicating and understand one another better. So we want to go beyond writing eventually. Um, as for the numbers, the Grammarly team is about 400 people across offices in San Francisco, New York, Kiev, and Vancouver. We're used in over 2,000 institutions and enterprise clients. And we have over 30 million daily users using the product across all interfaces that we support. Um, and Grammarly's most popular product is actually its web extension, which allows us to offer suggestions wherever people are typing. And Grammarly has been on the web a lot longer. So when we started mobile in about 2017, we wanted to take the same principle and we wanted people to be able to use the writing assistant wherever they are typing. So instead of actually coming up with an app which people have to open and then type in and get their text checked, uh, we followed the similar principle as a browser extension, and we decided to build a keyboard. And the keyboard allows us to have the writing assistant available wherever people are typing on their phone. And this has exposed us to some pretty interesting challenges, which I'll cover in my talk. And with this, let's get into today's topic, which is Grammarly's Android keyboard. Um, I'll start off with an intro to like what are the important pieces you think about when you're implementing a keyboard on Android, or what the Android documentation actually calls an input method editor or an IME. So on Android, a keyboard is an input method service. So it's a service as opposed to a different app, which is not an activity or a fragment. So you have to implement and register the service in your app and in your manifest. And that's how, like, when you install the app, the package manager knows that you're actually adding an input method service. You also implement a keyboard action listener to get callbacks for all the user actions. And so that's on one end. So those are the interfaces that you implement. And on the other end is the actual text editor. So that's where you send the text to. And that is represented by an input connection interface. And this interface has APIs that allows the IME to make changes to like any part of the text in the text editor. Um, One thing to note is that all calls to the input connection to the editor are IPC calls. So some of them could have like a really long round trip time. And so we have to use which APIs we actually use of this interface very judiciously on when to call them. Um, and generally speaking, as far as features go, the most common things on most Android keyboards are the keyboard layout itself, and where there are the keys, and then you have a suggestion strip on top where the IME tries to give you suggestions about like the word that you're typing or next word or like autocorrection, for example. And most keyboards have on-device models that do this. Um, so when it comes to the Grammarly keyboard in particular, we have all the features of a basic keyboard uh, that are required for text input and emojis as well. And what we do in addition is we have a connection with our backend for deeper sentence and paragraph level analysis of the whole text. And like similar to other keyboards, we also have models that are stored on device that come with the app. And we use these for things like autocorrection, current word prediction, next word prediction, autocorrection. We also built our own swipe to type gesture recognition algorithm for users who are used to that mode of input. And what we also added is an on-device model for suggesting synonyms, because like again, the goal of a writing assistant is to be able to suggest like different types of words, the variety of words that you might end up repeating a whole lot. So we wanted to offer alternate suggestions for synonyms as well. Um, so broadly, the keyboard, what you see is actually a fairly static UX, UI, and it mainly consists of, like I said, a suggestion strip, a keyboard layout itself. Uh, and what we also added is a revision mode, which takes place of the keyboard layout for certain use cases, which I'll go into. Um, and the UI itself is pretty interesting for a keyboard, because in other apps, as you add features, you can keep adding additional screens that the user can navigate to. Real estate is usually not a concern. However, for a keyboard, the only real estate you have in the most commonly used interface is the suggestion strip on top. Um, and for Grammarly, we make very heavy use of this suggestion strip. As you can see from the GIF, there are a lot of things that go on for like providing suggestions to the user. So as you're typing, you get different suggestions, three of them from the on-device models. And then whenever there is a suggestion from the backend, a stack of cards shows up from under the G logo. And then if there are emojis, they slide in from the right. And then there is also synonyms that show up. So a lot of things going on in the suggestion strip. And the view hierarchy is actually made up of a number of views. So then there is a stack of what we called alerts that come in from the left. And if there are multiple, they actually stack up. Then there is the Grammarly logo button, and there is a badge on top of that that show you the number of alerts. And then there are three words or phrases that we suggest, and that's common for most keyboards. And then there are emoji views that slide in as well. And once the user has paused for a few seconds, as you can see in the GIF, um, the suggestions are actually replaced with a list of synonyms. Um, and additional thing that is not shown in this GIF is there are also user prompts, um, because unlike other apps, there is not really a whole lot of room to inform the user or show prompts within the app itself. And people are very sensitive to uh, like showing prompts as they are using the keyboard, because this is a very uh, frequent but short sessions. Uh, so as you can see, all these views, they coexist on the suggestion strip. And then uh, as we have to be very careful about the transitions, because like something that's used 80 times a day, even like small micro transitions in the UI become noticeable as people get used to it over time. So it either becomes annoying or people form a habit of it. Um, so which is why the suggestion strip is really the workhorse of our product. Um, and this is how it actually looks when you inspect it through Android's Studio's layout inspector. So there's a lot of views overlaid on the suggestion strip itself, and each one of them has like a specific transition that happens on a specific event. Um, and in the interest of time, I won't go into the keyboard keys itself, because that's fairly uh, generic for keyboards, where although it seems seemingly like static, but there's a lot of things happening there as well, where for each key press, the key pops up, and for like there's also a view which overlays suggest like this gestures that people do for swipe to type input. Um, what I'll jump to is what we call a revision mode, which uh, gives the user an explanation of the suggestions from our backend. And so we had to build this so that we can offer for users who are interested in knowing like what the backend alerts actually are for. Uh, this overlays or this actually replaces the keyboard view with a list of cards. And so a few things happen here. One is when a particular card shows up, um, it highlights the corresponding text in the editor box itself, and that happens again through the input connection interface. And you can even apply changes to the text directly from here. So, and again, that happens through the input connection interface. Um, and when there are multiple suggestions, the cards actually line up. So this is implemented using View Pager 2. Um, so you can scroll through all the suggestion cards, and then the selection of the text actually changes per card. So we set selection depending on where the corresponding changes are suggested. Um, so as you can imagine, a lot of things go on for each key press. So I'll try to highlight a few of them. The main thing that happens is we immediately send the key to the editor. So if you press a G, like the G shows up in the editor. And then in parallel, the keyboard also fetches suggestions from on-device models for next word prediction or current word completion or autocorrect. And they are sent to the view models through an RxJava pipeline. Uh, and then in parallel, since we also have a backend connection, we send text changes to the backend for deeper like analysis of the whole text. And I'll go into in subsequent slide how that communication works as well. And all of these suggestions from the on-device model as well as from our backend merge together through as RxJava streams, and basically depending on particular events and like what comes in from the backend, or if it is like a synonyms event, the UI transitions accordingly. Um, and so this is the pipeline for like generating and getting uh, suggestions. And so there is another interesting challenge which could, I think, is unique for the Grammarly keyboard, is that the backend suggestions actually apply anywhere in the whole text. Most keyboards usually concern themselves with only a few words near the cursor, whereas for Grammarly's keyboard, depending on the text, we might want to change something which is a whole paragraph or like a whole sentence. So this is actually quite challenging because of concurrency. Say the user is applying a inline alert from the keyboard on top of the suggestion strip itself, and that could apply like 3 sentences behind. So you need to keep uh, a concurrent map of what is actually in the editor as well as in the keyboard. Otherwise, there could be challenges where a key press and an alert applying happen at the same time, and that could end up corrupting the text. And while there are APIs that allow us to get the whole text from the editor at any time, again, these are expensive IPC calls, so you have to be very judicious of, you can't keep getting the whole text all the time because that would like slow up, add delays to your interface. So we have to use tricks to actually make sure we are concurrent, we keeping like parity with what is in the editor. Uh, so the overall architecture of the app is uh, split into two. So when we package the app, it actually comes as a companion app, and the keyboard itself. And uh, I'll spend a bit of time on the companion app. So that takes care of like your onboarding, where you open the app and you go through registration, and then you have to walk the user through like enabling the keyboard, take them to the settings page where they switch uh, input methods, um, and also like there's multiple steps to actually select the keyboard that uh, the user ends up using, and that's part of the companion app that the app comes with, and that's part of the same package. But those are like traditional activities and fragments that um, mostly what traditional Android apps are composed of. And there's also a settings page as part of the companion app, where you can change parameters and properties of the keyboard. Um, and so when it comes to the keyboard architecture itself, we're trying to build a state machine driven architecture, because we found that like there is no particular MVVM or MVI pattern that applies to the keyboard. And we're trying to build uh, like states for the suggestion strip itself, for the keyboard view and the revision mode. And we're trying to get inspiration from like known patterns like MVVM, MVI, and come up with a state-driven architecture for this. Um, but basically what we're trying to do is make sure we have modular interfaces that are testable. And we don't have uh, actually a dependency injection framework, but what we're doing is trying to come up with our own cheap dependency injection, where instead of like initializing a variable inside the constructor itself, you take it as a parameter. So you can build on top of these modular interfaces, when then eventually we might end up adding a dependency injection framework in there. Um, yeah, so next would be the backend communication. So uh, we have a backend connection to our server APIs, and for text check we use a WebSocket connection that stays open through the session. And to communicate text changes, we use a protocol that it's an open source protocol called Quill Deltas, and it primarily comprises of three operations, which is insert, retain, and delete. So using these three operations, you can communicate like any changes to your document, and as you can chain them. So for example, uh, say you start with a blank document and you type hello with three L's. And so for a blank document, that would be an insert operation. And then you say you want to correct the spelling by removing one of the L's. So you can chain the retain and delete operation, where you retain the first four characters and then delete one of them. And so we batch these uh, operations on the client, and then periodically we send it to the server, and the server then sends us like suggestions depending on what is the current text. So we batch them so that we don't have to keep making like these calls for every character. So one of the most important things to consider when building and maintaining the keyboard is performance. And we think of performance mainly in two ways. Uh, One is the keyboard start time, uh, which is the time it takes for the keyboard to show up. And the other is the per key press latency. So in start time, there are three ways to break down the metrics. One is the cold start, where the keyboard process actually starts up, you load everything in memory, and then it basically starts living as a service from that point on. Uh, then there is a warm start, so which for a keyboard, we're trying to guess like what constitutes a warm start. So we're trying to optimize on all start operations for a warm start right now. And then there is a hot start, which is every subsequent session after it, beyond the point where everything is already loaded in memory. Um, and then there is per keypress latency. This is interesting because it's not just the time it takes for the keyboard to process that key itself. So that would be just taking the key and then giving it to the editor. There is a lot of UI transitions that happen at the same time as well. So the way we are thinking about it is we're trying to optimize for utilization of the UI thread. Um, and like we're trying to experiment with moving more and more things out of like what happens on the UI thread to like background threads, and that is how we're trying to improve per key press latency. And finally, there's memory utilization. So a keyboard is a service, unlike like an activity or a fragment. So it's a long-running process that might not actually not restart for a long time. So the memory utilization can also build up. So for example, we noticed that after a while, if we generate a lot of candidate suggestions from on-device model, the allocations and the data structures that we use for these, for like coming up with these suggestions can quickly add up if we generate a lot of candidates. And so halfway through a sentence, then there could be a garbage collection event which will just freeze your keyboard UI and the keys appear stuck. So that's one of the things we're optimizing on is how we like allocate memory and how we keep track of memory utilization. And finally, there's testing. As you can imagine, testing a keyboard with all these non-app constructs can be quite interesting. So we use a combination of strategies. One is we use manual testing for more exploratory testings where testers can play around with the keyboard and find corner cases. Um, since manual test cases we've found don't scale well with the like the more features you add. The number of things to regression tests can actually increase non-linearly depending on what you're testing, and things like the cursor position, the word before and after the cursor, and like variables of the particular feature itself. So that adds more and more complexity with the addition of new features. So we're building our own automation framework for that as well. And we found that instrumentation tests are quite challenging for testing a keyboard service, because in the documentation it suggests you get a handle to the service's local binder and then call service APIs on that object. But we found that for an input method service that actually does not work. And so for emulators 29, API 29 and up, we can't run instrumentation tests on it right now. So we're trying to run them on emulators that are API 28 and below using a deprecated service test rule. So we're mainly now relying on UI automation frameworks that we're building in-house with UI Automator, because again, with Espresso, you're testing the app that's in focus, not really the input mechanism. So we're using UI Automator to be able to exercise a lot of regression test cases. And then as these test cases add up, the length of your testing cycle increases. So we're trying to run multiple things in parallel using a framework called fork, which you add as a dependency on your test framework. And then it will, on its own, split the test cases that will run in parallel on multiple emulators. So then that's how we're trying to keep our test cycle short. Yeah, that's pretty much all I had for describing the keyboard itself. One thing I would like to say is we're a small team, so we're hiring. So if you're interested, if any of this uh, like found interesting, don't hesitate to reach out to any Grammarly team member. And thank you for listening. And I would love to answer any questions that you have. Okay. Um, how does the keyboard handle users that are offline? So for users that are offline, basically there are no backend suggestions that we get. So all the only suggestions you can actually get are that are provided by the offline models. Um, for example, like autocorrection, next word prediction, and synonyms, swipe to type. So whatever the keyboard does offline, those are the only things that the user will get. And like there is a badge that shows up on the Grammarly icon for showing that the keyboard is currently offline. Uh, so next question is, during the development, was it considered to use something like Kotlin multi-platform, or does iOS offer extra limitations? This is something that we've been thinking about recently. We haven't honestly thought a whole lot of Kotlin multi-platform, but there are things and logic that we can extract out that could be common between iOS and Android, and that's something we would like to explore. On iOS, though, there are a few other limitations where on Android, the API actually allows you to get the whole text from the editor, whereas on iOS, it is a little more restrictive, uh, where you only have visibility into a few words. So probably not, we can't do a whole lot of multi-platform or like commonality there, but there are other, like there is a lot of logic in both apps that we could extract out as common. So the next question is, sounds like you'd be debugging between two different processes. Are there any issues that come up? Um, so I'm going to take a guess here that one process is the keyboard and other is uh, the editor app, because the companion app and the keyboard are part of the same process. So if that's not right, maybe you can have a follow-up question. But uh, we typically debug within the same process itself. Uh, and the next question is, what are the efficient data structure algorithms that you use? You mentioned efficiently is the key to your use case. Um, so instead of like key data structure algorithms, what we're focusing on is basically making sure that the number or the amount of memory that is used is not rising a whole lot that leads to garbage collection. Um, and for efficient algorithms, uh, we basically so there's different parts to it. So a lot of the offline models, they generate all the candidates. So there are a lot of like NLP, popular NLP data structures that we use there for different suggestions. That's part of like a C++ library that comes with the app. And there's a lot of data structures used that are pretty common for efficient storing of dictionaries, or like traversing a word graph. So you can pretty much generate candidates in like logarithmic time. And so there's different strategies for improving efficiency depending on what you're trying to optimize on. But the key to performance optimization, what we've discovered, is it's important to measure it first rather than going by hunch. So what we're trying to do is we're actually measuring it and then making sure that we're optimizing for the right use case. Uh, Next question, as a follow-up, are the local models updated with suggestions from the server when online, or are the local models static? Um, so the local models are pretty much static. So as the suggestions come in from the backend, they actually are exclusive of what the offline suggestions that are generated. So there's no, like, both of them serve two different purposes. So the offline models are typically for things that are required at every key press, which for which a round trip call would be expensive. Um, and so the models itself, the suggestions from the model itself are not updated from whatever the server suggests. Uh, Next question is there a voice to text feature in the keyboard along with the correction suggestions? So there is a voice to text feature, but the way it works is you that uses the Google API to transcribe the voice and then generate text out of it. And once the text is in the editor box, then we check the text and offer suggestions on it. So we don't actually correct it during the transcription phase. Uh, the next question is, users tend to have high expectations for keyboard features. How does Grammarly balance the priority of building these often complicated features? Um, so it is a combination of um, basically product priorities, business use cases, and also like what is the possibility of engineering. So we use like a lot of things to decide on what to build and what not to build. And given that it's a small team, we have to do this quite frequently on like how do we ensure we are working on high impact use cases, because you could end up building things which are useful for like a small set of users that not that couldn't have a higher impact. So we basically work with very closely with our product team on figuring out what should be the priority of building what features. So for example, in the past few quarters, uh, initially the keyboard didn't actually have swipe to type. So given that it's one of the most popular input methods used for Android, we end up building, even though it was a pretty complicated feature, it was essential for us to have feature parity on Android as a keyboard. So that is where we invested resource in making sure we are able to build and ship that. Um, the other one on Android, what we did recently is we have a lot of international usage, and switching keyboards on Android is actually tricky given what OEM phone you're using. So on some OEMs, the switching keyboards might be straightforward, but on some phones it might not be. So we also offered like typing in native languages. So that is something uh, we invested in making sure that people are able to use Grammarly, but also switch to a layout where they can use their own native language too.